Good evening, ladies and gentlemen. It's a great pleasure for me, but also a great honor to welcome Rashid Sunyaev here for this talk. Rashid was born 1943 in Tashkent, Uzbekistan. From 1960 to 1968, he studied in the Moscow Institute of Physics and Technology. In 1968, he was becoming candidate of science. This is the equivalent of a PhD in the American-European system. 1973, he is Doctor of Science, which corresponds to a professorship in the Western system. Then from 1974, he was entering the Space Research Institute in the Academy of Science from USSR and later Russia. From 1982 to 2002, he was head of the High Energy Department of the Space Research Institute. From 1992 onwards, up to today, he is one of the chief scientists of the Space Research Institute. 1996, he was becoming director of the Max-Planck Institute for Astrophysics. And 2010, he was becoming visiting professor in the Institute of Advanced Studies in Princeton. Professor Sunyaev has a very wide field of research. On the one side is cosmology and the microwave background, and he will speak today about this, including the clusters of galaxies. Then there is a strong theoretical side of astrophysics in his research and the high energy, and especially the accretion onto black holes, the theory of it. And this I would like to mention. It is different from the topic of the talk, but it is more overlapping with my work and the X-ray observation. In 1973, Sukura and Sunyaev published a paper with black holes in binary system observational appearance. This is one of the most fundamental papers in modern astrophysics. It has today 5,881 citations. This is the sixth most paper, and it is a theoretical paper. People making clear explanation. If you look to the cosmology from the side of energy, there are two main mechanisms driving our understanding. On the one side, the fusion, which explains the stars, and this was a physics from 1930, 40, 50, 60, and 70. And then is a big different mechanism, and this is accretion onto compact objects. And this is a major part of our modern physics with active galactic nuclei, black holes, neutron stars. And the fundamental mechanism in this is an accretion disk, and this was introduced by Sukura and Sunyaev in 1973. And therefore, I am very glad that he is here today and speaks about a very actual theme, the microwave background and the clusters in it as we see them.
Thank you. It's a great pleasure for me to be in Madrid again. It's a great city. I arrived yesterday, and I was just enjoying walking in this vicinity because the city is absolutely great. And I will speak today about work which I was lucky to do when I was very young, and what is now observed by Planck spacecraft, by South Pole Telescope, Atacama Cosmology Telescope, and many other instruments. I will tell you a few words about them, and the main discovery is made now by all these telescopes, and for example, this cosmic microwave background, I will speak about it. These clusters of galaxies in microwave spectral band are visible like holes, just brightness like negative sources. And this was very old prediction, and now people are observing, and I can tell you that more than 1,000 sources are discovered on the sky with such properties. You see this deep hole in CMB. This is what I will try to speak today about. Before I will start, I will remind you what is the redshift. I understand myself that people who are coming to the lecture about astronomy or space research, they all know what is the redshift. But just I will remind you this simple picture from Wikipedia. When source, for example, star, is recessing from us, then we see that all lines in the spectra of elements are redshifted. They go to the longer wavelengths. If object is coming to us, then due to Doppler effect, we see shorter wavelength, light comes to us with the shorter wavelengths, and we see this also. This is a definition of, astronomical definition of redshift. 1 plus redshift z is observed wavelengths of the line to emitted to the what objects emits in its rest frame. And this is great that we can measure the velocities and direction of velocities by this method. And this is the reason why Edwin Hubble was able to find Hubble law, which is showing that recessional velocity in nearby universe is proportional to the distance. And at the same time in cosmology, when I'm telling that this object is very far from me, I am telling that that object was leaving long ago, because time takes, it's necessary to have time to reach me if object is distant. Therefore, redshift for me, for this talk, will be also the signature of the age. But age not in the time how long radiation is coming to me. But I will be very interested in the time from Big Bang to the moment when this object was formed. I will be mainly speaking about this. Yes, now about clusters of galaxies. What is it? This is great, let's say, propaganda slide of Hubble Space Telescope. One of the greatest images professional astronomer can see. You see here in one place, but this in reality, this only central part of the cluster able 20 to 18. But in normal clusters of galaxies, we see thousands of galaxies simultaneously, 1,000, 2,500. And these galaxies are moving in the common gravitational field, in the common gravitational well. And this is very important, that velocities, how they are moving, are of the order of 1,000 kilometers per second. Not per hour, but per second. Huge velocity. And this is very, very important. Second thing why we know that there is huge gravitational potential, we see with X-ray telescopes like XMM telescope, like Chandra telescope, we are observing hot intergalactic gas, and temperature of this gas is of the order of 100 million degrees. 100 million degrees is a huge temperature. We dream to have it, for example, in tokamaks, to organize the fusion reaction on the Earth, to solve our energy problems. But here we see gas of the same temperature. Additional, and it is possible to keep this gas only if you have huge gravitational potential. This gas forms something similar to the Earth's atmosphere. And you know that there is height of the atmosphere, 8 kilometers, because temperature immediately provides us how far from us gas can be if it has this temperature. Because, but gravity of Earth is negligible, here gravity is great. You remember that sound velocity in our in our atmosphere is close to 1,000 kilometers per hour. Here it is 1,000 kilometers per second. Therefore, gravity is 3,600 times square stronger. It is 10 million times stronger gravity. But we can study the gravity of the clusters of galaxies using gravitational lenses. Look to these objects, these. You see that these are galaxies, but these galaxies have very strange form. Look here, and they are going on the same line. This is the result of gravitational lensing. You heard about the Einstein work on this problem. And all these galaxies which I showed you now, they are situated much farther, much behind the cluster of galaxies. And their light is amplified by gravitational lensing, and then we are using Hubble Space Telescope and amplifying it again by usual optics. And this gives us possibility to observe extremely distant galaxies. Therefore, when a new, very bright cluster is discovered, all optical or majority of optical astronomers are happy because they can study these very, very distant objects well behind the cluster of galaxies. We can continue. I will speak a lot about these clusters of galaxies because they are now becoming extremely important for cosmology. In reality, greatest discovery was done in 1933 by Fritz Zwicky. This was Swiss scientist who immigrated to the United States and was working in California Institute of Technology, which had already at that time the biggest telescopes in the world. And he was great master, not the best character, but great astronomer. And Fritz, you see here already that character is visible on the face. And Fritz Zwicky did very simple estimate. Scientifically, we can say he first used virial theorem to infer the existence of unseen matter, what is now called dark matter. It's coming from Wikipedia. In Wikipedia, if you are wrong, tomorrow somebody immediately changes what you have written and writes his own truth. And I know that this paper, without any changes, is already 6 or 7 years. Majority of astronomers agree with this. And what he did, just knowing only course of the high school physics, we know that this Jm over r, if m is the mass of the cluster of galaxies and r is its radius, we can estimate what is the gravitational potential. It is it. And this gravitational potential should be of the order of v square. Velocity, the energy is also mv squared divided to 2. Therefore, mass should be of this value, and Fritz Zwicky showed that this mass is huge, very, very high mass. Then he was great master. He was able to estimate masses of all visible galaxies here, and result was astonishing. All stars inside galaxies in this cluster of galaxies had mass more than 10 times smaller than dynamic mass, which is coming from this estimate. And he told this in 1933, and nobody believed him, because everybody believes that everything should be simple, and everywhere is normal matter, which we see. But from 1933 to the end of 1960s, a lot of people tried to disprove him, but nobody was able. Everybody was getting the same result. Or they had very big error bars. All the best people were getting the same result. But were silent because this was not very good. But what occurred further people found today, we know at least with 5 different methods completely different, not only having clusters of galaxies. We know that there is this missing dark matter, and this dark matter is much more abundant than normal atoms from which everything around is built. We see, first people thought, and at that time, we also thought that maybe this gas is the hot gas inside clusters of galaxies. Now spacecraft, like European spacecraft XMM, are measuring properties of this gas. And in the same cluster where Fritz Zwicky made his discovery, gas has temperature of the order of 100 million degrees. Huge temperature. But density is extremely small. Only 3 electrons, only 3 electrons per 100 cubic centimeters. Very, very low density. This is just vacuum. Vacuum which is extremely difficult to get in our physics lab. So strong is the vacuum. But because volume is huge, this volume, megaparsecs, therefore we see very bright X-ray emission, and it's very easy for example, XMM to study it. Mass of the dark matter there is 15 orders of magnitude higher than mass of the sun. It's huge mass. And what is important to say here, that sound velocity of the gas, of the hot gas, is very close to velocities of galaxies. This means that galaxies are moving inside this gas with subsonic, sonic, or supersonic velocities, depending which galaxy we are observing at a given moment. And today, having all existing data, we know following, that stars contribute only a few percent of total mass of the cluster. And it is few percent, and Zwicky was telling that amount of mass in stars is 40 times smaller than total mass. Today, it is practically the same. He was really giant that he was able to observe this. 15% of mass is in normal gas, but very hot gas with 100 million Kelvin. We see it also. And the last contribution is dark matter. These are simulations. We cannot observe this dark matter, but indirectly we know that it exists because we see how galaxies are feeling its gravitational field, how the light from distant galaxies is feeling gravitational field of this dark matter. This is giant discovery, and you see, we see now hundreds of clusters. We have information about hundreds of clusters of galaxies, and everywhere practically a ratio is the same. It's very good and interesting. Second grade, I was very lucky when I moved from elementary particle physics to astrophysics. Just after several months, the great prediction of George Gamow, Russian physicist working in the United States, was fulfilled. Penzias and Wilson, they got Nobel Prize afterward for this, discovered radiation which is filling our universe, this cosmic microwave background radiation. In every cubic centimeter of our universe, everywhere, there are 412 photons which came to us from Big Bang, practically. In reality, from redshift 2 million. At 2 million, there is a black body photosphere of our universe, but it's a different subject. I can speak a lot about this, but let us say that these are very relic, very old photons, like dinosaurs, but alive, they are coming to us. And this radiation is great. American spacecraft COBE and FIRAS instrument, this also is Nobel Prize of John Mather, was able to measure black body spectrum of this radiation. Spectrum is extremely good black body, as Planckian formula predicts. We see this on the sky. Till now, nobody was able to find any deviations from black body. Just our sensitivity is not enough. And temperature, we know of this radiation, we know it is 2.725, 2 degrees, 725 millikelvin. And precision of this measurement is 1 millikelvin today. It's not enough for us. We are asking to measure more precisely, but for this it's necessary to prepare extremely sensitive spacecraft. Technology permits already. This is a map of angular fluctuations of CMB and obtained by WMAP spacecraft, absolutely great spacecraft, which blue points here are more dark than average radiation to 200 microkelvin. It is 4 orders of magnitude dimmer than average sky, just the brightest spots, the dimmest spots. And the brightest spot, red, are 200 microK brighter than average temperature. This was sensation, and I can tell you even more. Boomerang flights, Maxima balloon flights, they found this before WMAP, but WMAP made all measurements so precise that today only Planck spacecraft, European Planck spacecraft, has better sensitivity. We will know in 3 weeks. There will be press release with new data of Planck. I cannot speak about them now, full embargo, but I can tell you only one word. Planck is significantly more sensitive than WMAP. And what is important also that these, dim and bright places, these are the traces of acoustic waves, standing acoustic waves, which were existing in our universe when it was younger than 400,000 years. There were acoustic waves, and we see these traces today on the angular distribution of this radiation. Why am I speaking so long about CMB, about this radiation? It was discovered in '65, and maybe 2 years later, when I first time heard about from Samuel Kaplan about this missing mass of Zwicky, it was everybody was silent about this, but some people knew very old paper. And I told about this to Zeldovich, to my supervisor, and told him it's a great problem to find this dark matter. Maybe this is hot gas. And Zeldovich told immediately, okay, if you are interested in this, please look and find a way to see the traces of this radiation on the CMB. Maybe you will find something. I started to do this, and first what I did, I considered that maybe photon is coming, scattered to different directions, and I will see something. But in isotropic radiation field, there is always another photon which will substitute this photon 1 and will come to me. Cloud is invisible. I came to Zeldovich, told this, that I made this discovery, and Zeldovich told me it's well known 200 years. This is Tyndall effect, and when then I was unable to find anybody who knows about Tyndall effect. Finally, I found it is the following. When there is no moon, and there is, foggy environment, you cannot see the hot air which is coming from chimney. And when weather is good and there is moon shining from one side, you see beautiful, beautiful image of the gas which is coming, hot gas which is coming from chimney. This was Tyndall effect, that in the, in the isotropic environment, it is impossible to see the source and scattering source. I found the same independently 200 years later, and Zeldovich was only smiling. I was looking very long, and we were working together for maybe 20 years, and I can tell you that in reality today there are 3 effects. I will speak today about thermal effect, change of the CMB spectrum in the direction to the cloud with hot gas, which is observed in 1,000 clusters of galaxies. Second effect which we discovered is kinetic effect. Moving cloud changes the spectrum of scattered CMB photons due to Doppler effect. And we can see this, and we can measure velocity of every cluster of galaxies at that time with very high precision. It's like motion in the presence of a sphere. It is an interesting problem. And the third is the blurring effect. CMB in reality is not isotropic. There are angular fluctuations due to sound waves, you see here, and scattering in the cloud removes anisotropies in the direction to the cloud, except 10% of quadrupole at the position of a cloud, which produce polarization. These are three effects. I will speak only about first one. It was very long ago. I am happy that I survived, and I am very unhappy that my mentor, Zeldovich, is not here today. He died in '87, and he haven't seen these beautiful things which I am describing to you. He was a great scientist, and you see here he got 3 stars of hero of socialistic labor in Soviet Union. This was highest award. And only people who were doing atomic or hydrogen bomb were decorated with 3 times. Only one person, even Stalin, wasn't decorated 3 times. Brezhnev, when he was completely ill, he requested for himself more and got them. But before this, were only people who were creating weapons in the country. And Zeldovich had 3 of them. He was very brilliant person, and when he retired from his work connected with atomic and hydrogen bombs, he moved completely, decided to work in astrophysics and cosmology. It was a surprise for me because practically simultaneously in the end of 50s, in the 60s, a lot of people who were doing the same in America also moved also to cosmology. Everybody was interested what is the universe and how is it possible or not to do something with the whole universe. These people were especially interested in the Big Bang. You understand yourself, it was similar to their main profession. And also a lot of people who were doing radars, they went to radio astronomy. And these people were extremely strong with a lot of experience. And it was necessary for them to find good young people to work with them. And I was lucky to meet Zeldovich at that time. And there is a story because I was in elementary particle physics, and chief of my department, when he heard that I am trying to move to Zeldovich, he told me, you are a good student and you are clever young man. Please, why you are going to astronomy? Everybody knows that this is useless science. When I came to Zeldovich, I told him I don't like to do astronomy because it's useless science, as my professor told me. Zeldovich was much more clever than I, and I think even than my professor. He told me, it's okay, please help me with 2 small problems, and then we will return to the elementary particle physics. When I solved these 2 small problems, they were so beautiful that I never else even told him even one word that astronomy is useless. I was happy that I am permitted to work in that field. And whole life I was very happy with this. Okay, let's move further. What was the idea? The idea was the following, that if we have the line, this line is scattered on the hot electrons, here with temperature 55 million Kelvin. Electrons in such temperature are moving with velocity 1/7 of velocity of light. It's serious temperature. Therefore, it is necessary to look for all corrections. I took all corrections up to the 2nd order and found that right wing of the line is stronger than left wing. Photons, poor photons with very low energy is taking energy from the rich electrons, powerful electrons, and a little increase their energy. Therefore, they are moving toward higher frequencies. If I will take blackbody radiation, I can consider that this is the sum of many laser lines. Each laser line moves to higher frequency, you see here, and as a result, total spectrum becomes of this type. In the low frequency band, CMB at 1 centimeter, 10 centimeters, 3 millimeters, the brightness is decreasing, you see here. And in the WIN part of the spectrum, means behind 1 millimeter, we have increase of the brightness. This was very simple and beautiful. I had a lot of difficulties. For example, when I found formula for this spectrum after scattering, I discovered that in 1925, Paul Dirac was interested in the same problem, and he had different result. I was practically ready to kill myself because I spent many months of my life to get this formula, and then it is wrong, and it is published in 1925. Fortunately, after very careful reading, I found that Dirac himself is writing that he understands that his result is wrong, but it's not so important. He published, but he understood that his result is wrong. Therefore, it was okay. Today, this formula is used also to measure the temperature in tokamaks, just the same method. But we invented it much earlier. And prediction was that in place of the cluster of galaxy, there will be hole, just negative source. This was prediction, and prediction was rather strong and extremely unusual. I remember how I was giving talk. Zeldovich sent me to give talk in the Lebedev Physical Institute, and when I was describing these things, one person with absolutely gray head stayed and told me, "Young man," I was very young, "you even do not understand that you are completely wrong. According to Kramers, when we are observing hot gas, then the brightness should be higher, and you are telling that brightness should decrease. This is impossible. I am teaching thermodynamics and statistical physics for 35 years, and I am absolutely sure." And everybody was telling, "Yes, he is wrong. I was trying to say," nobody was caring. And then Zeldovich appeared in the room, came and told, "Oh no, Rashid is correct." And everybody started to say, "Yes, yes, yes." And then I recognized how important that heavy artillery is behind you, you know. Then you really in much better situation. I remember this because you cannot say anything. People just do not hear you. And Zeldovich appears and he only is telling that you are right, everybody immediately agrees. And I had another prediction, and another prediction was following. That this is a spectrum. That spectrum should be in centimeters and millimeters negative, you see here, negative source, and then it should be positive. And there is a frequency, 217 gigahertz, where effect should be exactly zero. This was prediction, that maybe sometimes some experimental people will find this. In addition, I found that effect is independent on the spectrum of the effect is independent on the redshift of the cluster, and that brightness of the clusters, central brightness, also doesn't depend on redshift. On this stage, every astronomer was against me because all galaxies are showing redshift. Hubble has his Hubble law, and now you are coming with effect which doesn't depend on redshift. Therefore, I had again difficult times, but finally people already agreed with this. But experimental conversation came only in 80s. I told you that all was done in the end of 60s and beginning of 70s, and only in the end of 80s, John Karlstrom from University of Chicago presented his observations of 28 clusters of galaxies. Here are 3, and he demonstrated that the brightness doesn't depend on redshift. Here redshift is 0.17, it's nearby universe, 0.54. Here cluster is residing from us with velocity of the order of 75,000 kilometers per second. And this cluster, 0.83, velocity is higher than half of velocity. Recession velocity, according to the Hubble, is more than half of velocity of light. But they were all absolutely the same. X-ray flux, look how it was decreasing. It decreased enormously for this cluster. Here, we had no difference. After this, a lot of people became interested, and I will speak today about Planck spacecraft, about Atacama Cosmology Telescope, and about South Pole telescopes. All of them have filters. Here, to see the negative source, here to see zero, and here to see positive. They specially choose filters to observe this thing. Angular size of the cluster is also very interesting. Cosmology showed us that the dimension, the same, if they have the same dimension, 0.5 megaparsec, then angular dimension is always of the order of 1 arc minute. You see, from redshift 0.3 to redshift 3, cluster should be of the same dimension. Therefore, brightness is the same, flux is the same, therefore, you can see that it very easily at very high redshifts. Now, Planck spacecraft, you heard about it, and in several weeks, there will be great press release of this spacecraft. They will demonstrate all discoveries, and also discoveries of enormous amount, a lot of clusters of galaxies, which Planck discovered just new on the sky. And main goal of this spacecraft in the science of clusters of galaxies is to check how the density of clusters of galaxies was increasing with time. It is study of the same type. If I have Madrid, I am interested, for example, how many people were living in Madrid during Roman time, how many were living in the Renaissance time, or in the Dark Ages, in the Renaissance time, how many were living during Napoleon invasion, how many in the beginning of the last century, during the war, and how many now. And you see that population is growing. Amount of clusters is also growing with time. And what is important that Madrid, population of Madrid is limited by amount of people in Castilla. Even if everybody will move to Madrid, Madrid will grow not too much. Then people from whole Spain are coming, from Argentina return, and so on. And clusters are also accreting matter which is around. Planck is working in excellent Lagrangian point 2, in the same point where WMAP spacecraft is working, and this point is excellent because Sun, Earth, and Moon are situated from one side, always from one side of the spacecraft. Its distance is 1.5 million kilometers to that point, and therefore this part of the spacecraft is always looking to the deep space, and therefore it is possible to make very easily passive cryogenic, passive cooling of the instruments. It's very good and useful, saves a lot of efforts. Now, some results of Planck, just observational. Look, this is known cluster Able 2319, seen by Planck from 44 gigahertz to 545 gigahertz. The deepest region was predicted at 100 gigahertz and 143 gigahertz. It's 2 millimeters. Zero was predicted at 1.38 millimeter. And there is nothing in the Planck picture. Here, it should be positive, and people see positive flux. This is a confirmation we really observe the cluster of galaxies. And Planck has these filters and can do this easily. This was very important. And I will show you also one of the greatest discoveries of Planck in connection with clusters of galaxies. There was special press release of European Space Agency. Planck discovered rather unusual object here. And when XMM Newton observed them, XMM Newton saw 3 X-ray sources here, and each of them are 3 clusters of galaxies, which each of these clusters has thousands of galaxies inside. But altogether they form first supercluster discovered by Planck. Planck has several superclusters now. It was very unusual discovery, and a lot of people now are studying this interesting object. If somebody here is doing plasma physics, people know that there are heavy Z ions, and heavy Z ions are have their own atomic physics and producing lines. In X-ray astronomy for us, it's very important to observe lines of the helium-like iron ion when iron nucleus has only 2 electrons. Charge is 26, but only 2 electrons left. In that case, energy of the line in the rest frame is 6.7 keV. Here you see this object, and you see that iron line is shifted. This is 6.7 keV, and iron line is coming around 5 keV. We can measure the redshift just using X-ray as X-ray data. You see, for example, here, object which has a redshift 0.94, practically 1, when all lines in the spectra of the galaxies are shifted twice. And X-ray line is coming to us with energy of the order of 3 keV. We can measure also redshift here, it's measured. This is object which Planck discovered 2 years ago. And this slide is showing you, presenting you the instruments which were specially designed to observe this effect. And here I am glad to show you Atacama Cosmology Telescope, South Pole Telescope, directly on the South Pole. There is American station, and big telescope, 10-meter diameter, is staying there. You see James Clerk Maxwell Telescope with Balakam instrument from Caltech, which is on Hawaii, Amoeba Taiwanese instrument on Hawaii, Apex German instrument, which is staying in Atacama Desert. This Karma and this Zeta Ray, they are in Owens Valley, from where the water is coming to Los Angeles. And the very big radio observatory. Even in foggy Cambridge, people are trying at low frequencies to observe this effect, and they are rather successful. And this is biggest American dish, GBT, with 100-meter diameter in Green Bank, West Virginia. All of them are spending a lot of time and efforts to observe this effect. And what are the results? For example, these are data 105 existing clusters, well-known clusters with redshift from 0.08 to 1.4. I can tell you that Karma has now a collection of the order of 400 objects. For them now, with new detectors, they will need from 18 minutes to 2 hours to detect and to measure effect in any new cluster which we will tell them. They cannot look them on the sky, but if you are telling them where to look, they immediately confirming you with much better sensitivity, because it is a rather big instrument. Planck has only 60-centimeter diameter dish, and here you see how many dishes are this interferometer. Yes, these are discoveries El Gordo. This is very interesting object discovered by Atacama Cosmology Telescope in Atacama Desert in Chile. 5 kilometers altitude. It's very impressive place. I was born in Central Asia. There are deserts, Kizilkum, Karakum, and everybody is telling, oh, this is very dangerous deserts. I was there. I can tell you that they are gardens in comparison with Atacama. Atacama is real desert. And if we go further, you can see here new cluster, this El Gordo, discovered by this Atacama Cosmology Telescope. This what Atacama Cosmology Telescope sees, 6-meter dish. It sees this hole in the sky. But in X-rays, Chandra spacecraft sees much more complicated picture. Chandra sees that there is a cold, relatively cold gas with temperature of the order of 70 million Kelvin is rapidly moving in this direction. And here is gas shocked by shock wave, and this gas has temperature of the order of 22 keV, which is 250 million degrees. Huge temperature. And it's interesting that for ACT, this is the brightest gas. And for XMM, this is the brightest. For Chandra, this is the brightest gas. And you see how all gas dynamics is here working. And one cluster is merging with another, and they collided with velocity of the order of 2.5, 3,000 kilometers per second. And internal gas has sound velocity of the order of 1,000 kilometers per second. Therefore, there is huge shock wave, and we see this shock wave and measuring this. And all this is occurring at high redshift because iron line is observed from this cluster. It has energy 3.56 keV, and redshift is 0.87. Universe at this time, it was more than twice younger than today. But we are observing everything because it was possible to detect this cluster. And I can show you how optical astronomers, we are telling them the position, and these are lensed galaxies discovered by Magellan telescope in Chile using the object discovered by Atacama Cosmology telescope. You see, these are lenses, Einstein lenses, beautiful, great, and they are very, very distant galaxies which Magellan telescope is able now to measure their redshift. Some of these objects have redshift 7, for example, or 8. These are most distant galaxies which we are able to observe. Now I will tell you a few words about this great instrument, South Pole Telescope, which is built by consortium of West Coast universities in the United States, mainly Berkeley, Chicago, and Santa Barbara, Stanford, Colorado, and so on. And Atacama Cosmology Telescope is a consortium of the East Coast universities led by Princeton. You know, just competition between Catalonia and, I don't know, Andalusia. It is the same. Yes, and what we can see here, this is great thing. Physicists know that here, not very far, somewhere here, is situated ice cube instrument. This cubic kilometer of ice as detector for neutrino and cosmic rays. And all this in the South Pole. South Pole is great because amount of water, precipitation, is smaller even than in Atacama. Therefore, it's possible to observe in sub-millimeter wavelengths. Great place. And you see how they are working. These fluctuations on the sky, which they observed, are the remnants of sound waves in the early universe. They see these sound waves. You see the traces. These two objects are bright, young galaxies or black holes, which have a lot of dust around and therefore are emitting in sub-millimeter band. Dust is reprocessing optical and X-ray emission. And look, here they see, on the same wavelengths, they see very deep negative source. 1 arc-minute dimension, and this is 15 sigma cluster detection. People immediately start to observe them, and they see, for example, as here, at 145 gigahertz, negative source, 225 gigahertz zero, and 265 gigahertz bright source. And this is exactly the signature of this effect. No one another effect can mimic this. This very peculiar spectrum. And this is a slide made during the polar night on the South Pole telescope. You see here is Milky Way. I hope that you see it. It's beautiful there, Milky Way. And this is the polar glow, not northern polar glow, but southern polar glow. You see it, it's a beautiful thing. And I was given, one of the people who spent there one night sent me his photo. I am very grateful to him, and I am in reality very grateful to all young people who are spending there this night. Because all of you know that in the polar night is half a year duration. Therefore, there only several people are staying there, and they're responsible for the normal work of the telescope, and there is no any, except, radio, there is no any connection with the mainland, with America, or even with Argentina or Chile. It's practically impossible that anybody can come there. There is no, at that time, it's impossible to land for planes. And people are spending, they're observing. I can tell you that I always was proud that I made majority of my founds during the night. I am late bird. But now I understand that it's nice to see at home in the night and to write your formulae when people are spending in such condition also one night, but half a year long. Yes. What we are doing, a lot of synergy between these instruments and obvious competition. Planck will give us all sky survey, crib of unique objects, like superclusters. SPT and TAC, South Pole Telescope and Atacama Cosmological Telescope have optimal angular resolution for detection. And all these instruments, GBT Mustang, Karma, ALMA, and so on, are producing for us details of the physics due to very high angular resolution. They can resolve the shocks by using this effect. What is the thickness of the shock? And it's very, very important. But let us speak now about cosmology. Let's move more close to cosmology. People are, when I'm speaking about this, people are telling me, okay, why people are spending their time and why funding energies are giving a lot of money for these instruments. Why it is important? First, when we have CMB data and X-ray data, they have unbelievable, they are producing synergy, and we can immediately measure Hubble constant using only one cluster, for example. We immediately are getting Hubble constant. As you know, astronomers are using tens of steps to get the distance scale, to find what is the distance to Cepheids, and then finding final Hubble constant. Here, we are using very simple thing. In fact, which I am describing, this is not by slide. Therefore, I copied, excuse me for this as that. There is, effect is proportional to temperature of electrons, which is huge, density of electrons, and dimension of the cluster. But X-rays are proportional to NE square and L. Now, it is not necessary to be a great mathematician. You immediately understand if I have two equations, I am measuring all these values, it is possible to solve temperature. I know from the spectrum of X-ray emission, it is easy to find both NE and L because there are two equations. From this, if I know NL, I can find what is the distance to the object, and at the same time, because L is distance is L divided to theta, and theta is angular dimension of the object. And this is the way how I can find, using for each cluster, what is the absolute distance to that cluster. This is a unique way to do this. People are trying. It's, as always, what is easy in theory, it's not so easy on the practice, because we are considering, when we were writing this formulae, we were considering that all cows are spherical. but we know that cows are not spherical, and therefore it is necessary to get information about dimension in one direction and in another direction. This is very old result of Bonametto, 38 clusters measured by BIMA radio telescope and Chandra spacecraft, and you see for each cluster the distance was measured. And this distance in gigaparsec, and this is redshift, and you see up to redshift 1, you can measure what is the absolute distance. You can scale our universe. Today we will have already more than several thousand clusters, and this will give us an almost new vision of the situation. And I can show you also our understanding of the universe. This is the Millennium simulation. It was done by Volker Springel in our institute in Garching in Germany. And Volker used the biggest supercomputer, third biggest supercomputer at that time, the biggest supercomputer which was created by Max-Planck for civilian needs, not for military. Therefore, it was smaller than 2 military computers. And you see here, it is not whole universe, it is, because these are simulation, it is narrow slice of our universe, 1/100th of its dimension. But when you see here, you see the structure, and there are knots of this structure. These are remnants, baryonic acoustic oscillations. These are remnants, again, of the same acoustic waves, which I told you. But there are knots of this thing. I have movie, but have no time to show it. You see every knot is a cluster of galaxies. In the center, there is cluster of galaxies, and this cluster of galaxies is growing because matter due to from these filaments, dark matter, and also gas are accreting to the cluster of galaxies, and mass of the cluster of galaxies is growing. Very similar to Madrid. There are, the roads, and people are coming every day to the walk to the Madrid. You understand this, and this is great city in the center, but this is cluster of galaxies. I can show you very old and very simple picture. When people were preparing experiments, which I showed to you, and they were trying to count how many clusters of galaxies should exist per 12 square degrees. This was a prediction of 20 years ago, and you can see here. It is in the case if there is only matter and dark matter in the universe. Everything universe is filled by dark matter and universe is flat. In this case, there should be no clusters of galaxies behind redshift 0.5. And we see a lot of them at redshift 0.7, 1, 1.5. This model is wrong. I remember when this was most favorable model, and I was telling to people it's against observations of clusters of galaxies. But at that time, only 3 clusters had a redshift higher than 0.8. Today we have several tens of them. And this changed the situation. This cosmological model doesn't work. This model considers that our universe is open, and there is dark matter, there is only dark matter and baryons, but density is 0.3 of critical one. And you see, this is the distribution. I can tell you, I cannot say you about Planck, but I can tell you that SPT and ACT and Planck in published data, they do not see no one cluster with redshift above 1.7. It's wrong because it predicts too many clusters at high redshift. And because the effect doesn't depend on the redshift, we should see them, and they are absent. Therefore, this model is completely wrong. And the model which is the best is this. Until now, everything seems to be okay. We will see new Planck data, but we are measuring how amount of objects is growing here. We should measure them very carefully, and then we will know both what is the amount of dark matter in the universe and what is dark energy. We can measure properties of dark energy if we will be able to get very good statistics of clusters of galaxies. I hope that Planck and this ground-based instrument will give this to us very rapidly. This is the distribution of clusters for their mass. In the case, if at the redshift 0, you see a lot. At the redshift 0.5, much smaller. At redshift 1.4, very small amount. It is 10 in power 15 solar masses. Coma is here, and majority of clusters which I showed you, they're above 10 in power 15 solar mass. They're here. And we see them. During last years, we discovered 7 of these objects. And in the best model existed today on the whole sky, they should be 20. Therefore, there is not whole sky is observed. Planck didn't deliver its data, but we are very close to prove or disprove the model. And this is the best model today which exists. And you see at redshift 1.4, when universe was 5 times younger than today, you see there were practically no clusters with mass higher than 10 to the power 15 solar masses. At redshift 0.5, when universe was had age 1/3 of the present day, or 1/2 of the present day age, you see the amount was much bigger. And today, you see, it's really, there should be a lot of clusters. And we can do this now, and we are computing this. These are instruments which were designed to observe these effects. People are walking high in mountains. You see these great animals, which is really possible to see in Atacama Desert. And it's very interesting. And this is the first results from Planck, and this is from South Pole Telescope. But I will tell you during the rest of my time, I hope that I still have time. 1 second. Yeah, I still have a little. And you see here following things. I will speak about the mission Spektr-RG, which Russia wishes to launch next year, in December of next year, to the second Lagrangian point. Second Lagrangian point, again, where Planck and WMAP are working, Herschel, and many other spacecraft. Our spacecraft will be continuously rotating around the direction to the sun. Revolution time is 4 hours. And in 4 years, we will make 8 full images of the sky. Then 3 years will be pointed observation. This is how there will be 2 deep survey regions, and this region will be covered quasi-uniformly. This is the platform navigator. Launcher which we got from Russia is Zenith Fregat. And there are 2 devices. One device, Arctic Sea, is produced in Russia with some participation of the Marshall Space Flight Center in Huntsville, Alabama. And main device is Erosita, which is produced by Max-Planck Institute for Extraterrestrial Physics in Garching, big experimental institute. I will show you rather unpleasant picture. We were fighting how to divide data. Finally, we decided to follow example of Portuguese and Spanish king. You know that at some moment when Portugal and Spain were the leading nations in the sea, they decided to divide sky. And I remember only that Portuguese king was not completely honest. He knew that there is already Brazil, and he asked to shift boundary a little to the west so that Portugal got Brazil. And there is one nation which speaks, you know this. Yes, and this will be the division between this part of the sky will be Russian, this part of the sky is German. Sounds not very pleasant, but we should divide in some way, and all clusters on this sky, part of sky, will be for several years belonging to Russian scientists and their collaborations. and this part to German scientists and their collaborations. Then we plan to unite the data because factor 2 is great thing. This is a great instrument which is built in Germany now, and this is 7 grazing incidence telescopes. You know, all of you, that X-rays do not have normal reflection. They are absorbing. Therefore, to reflect them, it's necessary to create hyperboloid and paraboloid mirrors, where you have photon is coming and then scattering this due to the grazing incidence with very small angle. And we have inside these mirrors very, very shells just to create the mirrors. And these are total surfaces, very big, reflecting surface here. There are cooling radiators, as I told you, and 7 giant CCD cameras, the biggest CCD cameras till now created for X-ray astronomy. They are built already, flight units. This is, you see, in each telescope we have 7 identical mirror modules and 54 mirror shells for each of these mirrors. Therefore, we have 300 or practically 400 mirrors in reality. I can tell you that when I was negotiating with German side what telescope we need, Germans told, oh, we have ready device, we were preparing it for American mission, but we lost the competition. At that time, I told, okay, what is the sensitivity? And we found that only 10% of clusters of galaxies on the sky will be discovered by that existing telescope. And I asked German colleagues, I told them, excuse me, we are interested to observe all existing clusters of galaxies in the universe. Only in that case it would be possible to get spacecraft from Russian side. We had long discussion. Finally, German scientists came to me, Günther Heisinger, and he and Peter Perdel, and they told me, okay, it is possible, but then you should give us much more weight, you should give us much more electrical power on spacecraft, so on and so on. I told him, this Russian spacecraft, no problem, Russian launcher. They got this and they created instrument which is able to observe to discover all clusters of galaxies in the universe. And this was great. You see here these shells, but and I told you already that clusters of galaxies were main design driving force. And what is important for us? We think that we will be able to detect 100,000 clusters of galaxies at redshift less than 1.5, because they are absent, or there are few of them at higher redshift. And what is important for us, that this will be all clusters existing in observable universe, up to our horizon. We cannot see further. Just impossible due to general relativity. And people told me, oh, this will be the end of the science because you will discover all clusters of galaxies, what to do further. I told them, look to Magellan, Columbus, to Captain Cook. They were discovering all islands in the seas. They discovered everything. Now with Google Map, we can go and look every of these islands easily. But science is continuing. Geography, physical geography didn't die. Geophysics is great. We cannot till now compute weather and predict weather well. This shows that I think that with clusters of galaxies we will discover something new, very interesting. These are recent computation. Will Erosita detect all clusters of galaxies? Yes, 100% for this 40%. You see. All massive clusters of galaxies in the whole universe will be detected. This is very impressive. Again, why it's important, but I can tell you also a few words about black holes, active galactic nuclei. We dream to detect 3 million active galactic nuclei on the sky and detect also traces of sound waves in the universe in their distribution, which I told you also before. Yes, and this will be these objects, how to make supermassive black hole visible. Gases falling, rotates around, and nearby layer have friction, and because they have friction, they are losing energy and angular momentum and slowly moving towards the black hole. Surface of the disk is heated because there is huge energy release, and black hole becomes brightest object in the universe. We can observe them very, very far. Today it seems that we are observing them up to redshift 8 rather easily. They are very, very bright objects. And we wish to detect 3 million such objects on the sky. It will be very interesting. And this is baryonic acoustic oscillations. We will find redshifts of all these objects. We will find these oscillations on the level of a few percent. And this will also give us additional information about properties of our universe in the early times. I can tell you that it will be possible to observe stars from 300,000 to 500,000 stars on the sky. Just coronae like our sun, but much more active. I can return to the black hole and can tell you that these black holes, to become the brightest objects in the universe, they need, the brightest of them, need 3 Earth masses to eat per second. They have very good appetite, you understand me. And per year, they are eating 1 solar mass. And it is very interesting when when star is coming very close to black hole, somewhere here. Due to tidal forces, it is disrupted, and black hole is not eating star as a whole, you know, just. It's important to make from it the gas, and then gas is giving you a lot of radiation. This is what black holes are doing and how they are eating. It's very important for us that there will be follow-up observations in optical telescopes and in infrared telescope and other X-ray telescopes like Chandra and XMM. We hope that they will be still on the sky and they will give us a lot of information, but most important are optical observations because they are permitting immediately to measure redshift of the objects which we will discover. And this is very, very important for us. And we are very happy that Spain has 10-meter telescope on Canarian, and Spain has also rather good share on VLT, on the great instruments of European Southern Observatory in Chile. And this was, I was telling you about clusters of galaxies. They are extremely important. And may I finish my talk with following words. We were waiting more than 30 years for the observations which will be able to prove our theory, which was created in 1969, 1972. I was very young at that time, this whole my life, as you see in science. Great progress of solid-state physics, cryogenic, technology of grazing incidence, X-ray mirrors, and bolometers, bolometers able to detect sub-millimeter sources of celestial radiation. Development of the spacecraft technology made it possible only recently. But it's possible, and I showed you thousands of objects which is today people are observing it. And I'm very grateful to hundreds of physicists, engineers, and astronomers who spent tens of years of their life and who made this possible. I thank them, and I also thank you for your attention. Thank you very much.